Okay, hello everyone. I hope you all had a nice lunch break and enjoyed your sandwich. Now we start with our next talk from our very own professor, Kenny Paterson, who runs the Applied Cryptography Lab here. And he will hopefully make you think more about those ubiquitous messaging apps that you probably have a lot of them on your phone, and you will find out differences that you probably don't know yet and maybe didn't want to know.
Okay, thank you very much. Thanks for coming. So I'm going to talk about secure messaging. Maybe we can start by finding out which secure messengers you are all using. So who's using Signal? Yes, fantastic. That's amazing. But I think it's a bit of a self-selecting audience, right? Who's using WhatsApp? Almost everybody. Who is using Telegram? Okay, stop using Telegram. Who is using Threema? Okay, interesting. I'm not going to talk about Threema today. I would love to, but I can't. But we will talk about Threema in the future. Okay, what other ones are there that I might not be aware of? Instagram, that's a thing. Yeah, some of you, a few of you. Okay, I don't expect ETH computer science students to be on Instagram. You're not visual thinkers, right? You're mathematicians or computer scientists. So I'm going to talk mostly in this talk about Telegram. But before we talk about Telegram, I'm going to talk generally about secure messaging, what the architecture looks like of a secure messaging system, talk a little bit about threat models and security goals. Then we'll do a little bit of a deep dive on Telegram, and then we'll have some closing remarks. Hi, come and grab a seat. I want to give a shout out here to lots of people. So this slide deck is based on a number of different presentations made by my research collaborators. So there's a list of names here of people that I've worked with on secure messaging over the last couple of years, and indeed, one of them is here. Kian is here. Nice to see you. I'm afraid you're not going to learn anything new, but it's great to see you here. Kian was a master's student in my group up until a couple of weeks ago, and we were analyzing a particular messenger together that I mentioned earlier that I won't talk about today. Okay, good. And then these are many other people, as I mentioned, that I've worked with. So Raphael Eichenberg was also a master's student in my group, and we analyzed Bridgify together, which was a secure messaging app designed for use in emergency situations where there's no network infrastructure. Unfortunately, it was really bad, and we completely broke it. But that was his master's thesis, and it led to a very nice research paper. So maybe like a sub message here is if you're an ETH master's student, is that many of you in the room? I guess quite a lot of you. Then you can come and do interesting master's projects with us or semester projects and get really interesting results that lead to really good publications. So if you're thinking about research as a future career, then we have quite a lot to offer you. And that's the only advertising I'm going to do. Okay, so let's jump in and start talking about secure messaging. I should say, before we get into that, you should feel free to interrupt and ask questions along the way. We have actually lots of time. Initially, I was only given half an hour, and it was at 2:45. And I found out at 12:15 today, I was sitting at home making my slides, as you do, right? Professors are always making their slides at the last possible moment. I found out that I was speaking now, and I actually had an hour. So my slides might be a little bit rough here and there. Let's see how they hang together as a slide deck. But we can make it as interactive as you like. I'm very open to getting questions. Some of them I won't be able to answer, but many of them I hope I can. Good. So let's talk about secure messaging in general. Here's some secure messengers and the number of users that they have. And I think an important characteristic here is the scale of these systems. So they have literally hundreds of millions or even billions of users, right? So WhatsApp currently, so these are from January 2022. In fact, Telegram is now up to something like 700 million users as of June 2022. So these are massive systems handling billions or trillions of messages every day. And we want to understand, how secure are they? Are they any good? Should we be using them for sending sensitive information that we might want to hide from our friends, our family, our partner, maybe if we're in a difficult domestic situation? Or we might be a person who's of interest to foreign governments. Maybe we have to cross borders, and then we care about whether our phones can be taken off us. What happens to the security of our messaging or of our old messages in that case? Is it possible that someone could take our phone off us, implant some malware onto the phone while we don't have it in our possession, and then give it back to us? And then we would end up with, malware on our phone, which then maybe starts exfiltrating messages back to some server, for example. So these are huge systems, and we want to understand their security. On the other hand, here's Edward Snowden. You're in great company. Edward Snowden says, I use Signal every day. So this is actually taken from the Signal website earlier this year. The sad thing is that Signal only has about 40 million users. So that's absolutely tiny compared to the scale of these gigantic messaging apps. What I will say is that the Signal design is widely used. In particular, the Signal design is used in WhatsApp, and I believe also in Facebook Messenger. Okay? I can't believe Facebook Messenger has nearly 1 billion users. I mean, who uses Facebook anymore? Anybody in this room still on Facebook? I hope, yeah, you are. Okay. Thank you for admitting that. I find, yeah. Anyway, I would, if you hold Meta shares, I would sell them, right? I mean, they're going. Have you seen their like Web3 play? I mean, it's just horrible. Okay, enough. All right. So Signal is this beautiful design that Edward Snowden uses. It has been very carefully designed by gifted cryptographers who knew what they're doing, and it's been formally analyzed and proved secure by academic colleagues of mine, people from my group. So it's a very robust and strong design. So it's quite nice that it's used in some of these other messengers. Now, have you heard of WeChat and QQ? These are enormous in China, right? Okay, good. So as far as I can find out, they have effectively zero security. So they, basically they have no encryption from end to end. We'll talk about that in a moment. But basically they have very, very weak security. And in a sense, they're not even worth looking at from a cryptographic perspective to try and find vulnerabilities or issues because they don't do anything interesting. They don't even try to be secure. But they're massive. And then you see there's a very important cultural aspect to secure messaging, right? In Europe and the US, we get to use things like Signal, and maybe those things are harder to use in other countries, other regions. So here's a typical architecture of a secure messenger. This is roughly what's going on. We have pairs of parties, Alice and Bob, classically, who want to communicate with each other, and they make use of a server in the middle there in order to ensure message delivery. Okay, so the server technically only needs enough metadata to ensure the message delivery and the consistent ordering of the messages at the receiver. In particular, the server does not need to be able to see the message contents in order to route the messages. And we talk about end-to-end encryption, or E to EE, or sometimes just E to E, when only the legitimate users, Alice and Bob, can actually read the content of the messages. Now, there's a lot hidden in this slide because, of course, you could argue, well, sure, end-to-end encryption is good, but what about security of the endpoints? What if an attacker can run monitoring software on my endpoint, or just takes the phone and reads the messages on the phone, right? So we might want to think about additional mechanisms there. It's also the case that in most large-scale messenger systems, you don't have a single server. You have a distributed server infrastructure with servers in maybe lots of different countries, different regions, for speed reasons, for scalability reasons. Obviously, so the kind of fundamental message here is that for secure messengers like Signal, the server only gets to see very limited metadata. And organizations like Signal have gone to great extremes to reduce the amount of metadata that they see. So that when they publish a transparency report, which they have to do, they can basically list very, very little information in their transparency report every year. Okay, so that's the general picture. So we want this kind of end-to-end encryption from Alice to Bob, but we might also want security for the transport between the client and the server, between Alice and the server and Bob. Okay, so here we call that C2S for client to server, but more generally there you might imagine using a protocol like TLS, for example, right? This is a classic client-server communication system, so maybe that's a good place to put TLS. You might wonder, why do we need the client-to-server protocol if we already have the end-to-end protocol? Well, remember, there is interesting metadata in the end-to-end protocol, right? The delivery address, for example, or some message sequence number or some ordering information. And we might want to hide that from external attackers as well. So actually so that's just, again, this is a very simplified picture of the kind of security concerns that we might have in secure messaging. Because, of course, there's all kinds of other features that a secure messenger might have. And I've put a list here. So we might worry about, how do we do user registration? How do we set up user accounts? How do we distribute cryptographic keys to Alice and Bob, maybe from the central server? If so, how do we authenticate that information? How do we know the server hasn't tampered with the exchange of keys that happens between Alice and Bob? We might want to think about contact discovery. So if I start a new messenger, how do I find out who else is using it in my network? You could just send all of your contacts in your contact book to the server and let them tell you the results, tell you which users they know about. Obviously, that has privacy issues. So we might want to do a more private protocol that enables us to do contact discovery, right? So in fact, Signal recently started using something called ORAM, oblivious RAM, which is a very nice cryptographic technique to minimize the amount of leakage from that contact discovery process. Backup features. So a lot of messaging apps, for example, Threema has backup features where you can basically, in a menu, press a button, and all of your old messages and all of your contacts and your key information can be encrypted using some key derived from a password and then uploaded to the server. And now the server is looking after your material for you, encrypted under a key that maybe the server doesn't know, but maybe the server could do dictionary attacks, right, to recover the password that was used to create the encryption key. Group messaging is extremely important and quite difficult to build. For example, Signal achieves group messaging simply by doing a bunch of pairwise key exchanges, and then basically everything is broadcast to everybody in the group. So that has kind of a quadratic blow-up in communication complexity, right? So this is not really very scalable, and for that reason, Signal has a maximum group size. Telegram, on the other hand, provides no security for group messaging whatsoever, but it can scale to groups of 200,000. Okay, so there's like a trade-off there between security and functionality, for example. We might want broadcast channels. Telegram has that. Multi-device support is extremely important, right? You want to be able to read your messages both on your laptop and your mobile phone. You have to maintain some kind of synchronization, and so on and so on and so on. Okay, and the basic message here is that this picture here is massively simplified, but it's all we're going to talk about today. Okay, but I do want to emphasize that there's this much broader set of features, every one of which has security consequences. So there's a massive attack surface when it comes to thinking about security of messaging protocols. It's not just this, it's also all of that. And for almost all of the messengers out there that we listed at the beginning, none of this has really been analyzed in a lot of detail. Well, that's not quite true. The key distribution authentication has been analyzed. There are papers about contact discovery, but most of the rest of it is really not very well understood by the research community, right? So people like me look at these apps, and we look at some of the features, and we try to find vulnerabilities and bugs or try to understand the security, but there's not enough of us to look at all of it. And that's why you should come and do a master's thesis in my group. Right? Okay, second advert. Second and last advert, I promise. Okay, good. So let's talk a little bit about threat models for analyzing secure messaging. And this is, Kian might recognize this picture. It's not exactly the same. You might notice I changed a word here. Okay, so there are three basic threat models that we can think about. There are others too, but these are the essential ones. If we think about communication from a client to a server, from a messaging app to one of the servers, okay, so that's this kind of client-to-server protocol, we might worry about an external actor, otherwise known as a man-in-the-middle or machine-in-the-middle or person-in-the-middle adversary, who's able to eavesdrop on the communication between the client and the server, and is maybe able to reorder messages on that channel, or delete messages, or modify them in some way. We think also about what happens if the server itself is compromised. So going back to this picture, what we want is to minimize our security assumptions for the end-to-end security of communications between Alice and Bob. So we want to trust in the server as little as possible, and we should ask ourselves the question, what if the server is compromised? What happens then to the security of our system? What can the server do? Does that seem reasonable as a threat model? Let's discuss it a little bit. Why should you not trust the server? Ideas? Thoughts? Yes?
I mean, because the servers are usually like managed by some company.
Mm-hmm.
In the case of WhatsApp, for example, not everyone is very trusting in what, for example, Meta would do with that information. So
right.
I want to hide that
mm-hmm.
from the company.
So you might want to hide the data from the actual company because they have privacy-invasive data mining policies. Facebook's a great example of that. Yes?
And this is a section that you can't verify. So, for example,
mm-hmm.
you have open source
Yeah.
It's really the code that's online. But even if you open source the software, you can never be sure that it's the actual code running.
The actual running code, yeah. I mean, you can address that kind of issue using things like SGX and attestation and so on, remote attestation, but it is difficult. And it's absolutely true that most messaging apps, many messaging apps have open source clients, so you can see the client software, and then you can maybe do some kind of binary transparency or something and trust that that's the correct code. But the server code is not open, so it's very hard to verify what the server is actually doing. You can send messages and see how it reacts, and you can try to kind of remotely infer what the server might be doing, but you can't actually tell. Indeed, I think yes, gentleman there.
In case the server is compromised, someone gains access to everything that was ever on there.
Right, exactly. Now that's a really good point. So it might not. We can trust the service provider, right? Maybe I trust Signal or I trust Telegram to run a secure server. But what I don't know is who else is able to compromise, say, Telegram servers. So you have this distributed server infrastructure. I'm going to show you how their cryptography works in a little while. What I want to say is if it's as bad as we think it is, what is their server security like? Are they any good at infrastructure security? Right? It's hard to tell, and we can't assess that remotely. Not easily, anyway. So the key issue is that maybe the server has been taken over by third parties who are trying to eavesdrop on communications between Alice and Bob, but by compromising the server. So it's good to try to think about what happens if the server is compromised, what security remains at that point. I mean, what possible organizations could we be talking about that might try to hack into the Telegram servers and get access to plaintext there? Who are we talking about? The elephant in the room, gentleman there. Government agencies, yeah, that's a good example. So national security agencies, or NSAs as they're known, okay, are very interested. Did you have another suggestion? Same. Another example is hacking groups who are interested in getting hold of compromising material that they can then use to blackmail people, or they can sell on the information market. Okay, so there are some very gifted hacking groups out there who probably are regularly trying to see what they can achieve in terms of breaking into these services. Good. So if you don't have this kind of strong end-to-end security and then minimize trust in the server, you don't really have any security guarantees. It's hard to be sure what security guarantees you have. Okay, good. And then the third, in this list, actually, the second attacker we want to consider is the compelled access threat model or attacker. So here we assume that the attacker has access to the unlocked device for some limited period of time. And the two classic kind of use cases here or situations that we're thinking about are, and I mentioned them already, number one is sometimes called intimate partner violence. Okay, so you're in a difficult domestic relationship and your partner is able to take your phone off you and look at messages on your phone or try to maybe extract a key from your phone that they could then use to later read your messages, okay? And then the second one is essentially law enforcement access or border agency access to your phone, right? So if you go through into an unfriendly country, depending on the law in that country, in fact, in the border zone, usually there is no law, right? The law of the country doesn't even apply there, or some special law applies. You can have your device taken off of you, and maybe you're forced to open the device, or maybe they put your face in a clamp and force you to not blink while they hold the phone to your face, right? If you have Face ID unlocking. Sounds crazy, but we want to consider the strongest possible adversaries and understand what security do we have for our system. Okay, good. So I think we'll skip this slide. It's a little bit irrelevant. Let's talk about Telegram. So many of you were using Telegram. Can we have a show of hands again? Are people still willing to admit it? Okay, we'll check again at the end, okay? Telegram is okay as long as you don't use it for anything sensitive, right? I used Signal. I try to only use Signal. Some of my family members are still on WhatsApp, but recently we all moved across to Signal. So there you go. Even my mum is on Signal. It's a very feature-rich messenger. It's a really nice thing to play with. It has all kinds of cool graphics and emojis and memes and nice website, 700 million users. Who doesn't want to sit with 700 million other people? Amazing. But we analyzed this system, we analyzed Telegram in detail, and we wrote this paper. So this is joint work with Martin Albrecht and Lenka Marakova from Royal Holloway. It's my old university before I came here. And also with Igor Stepanovs, who was a postdoc in my group up until 2021. So this paper was published at the IEEE Security and Privacy Symposium in 2022. And if you're interested in following up, that's the link that you need, the URL that you need. And you can read, there's like a high-level summary of the paper there. There's like us arguing with Telegram about whether the attacks are serious or not, plus the full research paper. So if you're interested in getting into the details, I recommend going to that website. I think MTP Sim stands for MT Protocol Symmetric, because that was the kind of scope of our research here. So here is a thing for the chart. Telegram is not the most important, although it has risen up the charts. So it's now number 4 in the world, say, in terms of scale. Why is it interesting? Well, another research paper written by the people from Royal Holloway examined the use of secure messaging apps in the Hong Kong protests from a couple of years ago. And actually, one of the authors here, Regge Bjerg Jensen, is an ethnographer. So she does information security in a kind of computer science environment, but her training is actually ethnography. So what she did was she went to Hong Kong and she, through various contacts she had, got in touch with some of the protesters in Hong Kong and interviewed them in a kind of structured interview format, and did about 15 or 20 interviews with different protesters to ask them about their choices. What messaging apps do they use? Why do they use them? What even is their threat model, right? So, what are they concerned about? And for a lot of them, the number one concern that they had was they wanted to be able to delete messages on other people's phones when those people were taken into custody, right? So they wanted to be able to basically remove evidence of communication. Okay, and a lot of messaging apps, some messaging apps have that feature, others don't. So they found then that actually Telegram was the predominant messenger being used in Hong Kong, and it was perceived to be more secure than all of the competition. It has some nice advantages. I already mentioned this. It supports group chats for up to 200,000 people. So if you want to establish a very large group, you can. And it has support for pseudonyms. So you don't actually have to register a phone number, for example, to use Telegram. Signal does require you to register a phone number. And it has lots of other really nice features. So it's very feature-rich. And that's an interesting thing. The focus, if you want to get market share in the messaging space, your focus really has to be on adding features, not adding security. So sometimes security can lag behind. So here is the Telegram architecture, and it fits exactly with the classical architecture that we talked about before. And I just want to point out that for the end-to-end security, it's not enabled by default, and it's not available at all for groups. Okay? So the number one reason why you should stop using Telegram is that it's not secure end-to-end by default. Okay, so you can switch it on because you're all security experts. You can find the relevant settings in all the menus and switch on end-to-end encryption. But probably most people don't. I don't have statistics for that, but my guess would be most people don't even realize that they might need it. Okay, so the default in Telegram for pairwise communication and the requirement for groups is no end-to-end security, which means all you have is the security from Alice to the server. So you have this kind of client-to-server protocol. And here, Telegram committed the cardinal sin of cryptography. They rolled their own protocol. Okay, it's called MTProto 2.0. Here, they could have used TLS, or they could have used WireGuard, or one of the noise protocols, lots of different options where the protocol is extremely well developed, security is understood, there are security proofs, etc., etc. No. Telegram knows better. They decided to use this thing called MTProto 2.0. Now, the naming here suggests that maybe they already had a problem, right? Because it's 2.0. So what happened? How did they get from maybe 1.0 or 0.99b or something to 2.0? Let's take a look at the history of the MT2 protocol. So this is really what I'm going to focus on now, and this is where the talk starts to get a little bit technical. So maybe a quick show of hands. How many of you have taken some kind of course in cryptography? Okay, fantastic. Almost everybody. Good. So I'm going to show you some of the crypto that's used in this MTProto 2.0 protocol. And we're going to be... So yeah, here is the history of MTProto 2.0. This is this client-to-server communication. It's the equivalent of the TLS record protocol, right? That's what it's doing. It's the part I'm talking about is not even doing key exchange and authentication. It's just assume that somehow we've done that, and now we want to encrypt individual messages using a symmetric key. How does it work? So they launched in 2013, and they had a protocol called MTProto 1.0, and it seems like this protocol was designed by the brother of the founder of the company. The founder of the company is a guy called Pavel Durov, who's quite famous in this whole world of messaging protocols. He also established essentially the Russian version of Facebook or LinkedIn called VKontakty. But then he was forced to leave Russia, and I think he now lives in Dubai. So his brother designed the protocol for him, and his brother was like a math genius, right? So great, mathematics must be good for designing cryptography, right? But then it was found out that actually the protocol is not what we call CCA secure, so it's not secure against chosen ciphertext attacks. This was an observation. Then people started to find bugs in it. So in 2017, Telegram released MTProto 2.0, and the only formal security analysis prior to our work was a symbolic analysis of this protocol, which proved that it's secure in a symbolic model. So in a symbolic model, many of you have worked with Tamarin, maybe, or something like Tamarin. Yeah, who knows Tamarin? Okay, quite a lot of you. So imagine here people using something like Tamarin or ProVerif to formally verify this protocol. But that kind of analysis assumes ideal building blocks. So they assume that the encryption is perfect. That means there's nothing really to analyze, right? Because how bad, the real interest in a secure channel protocol comes from looking at how the cryptographic components are composed to try to build a secure protocol. But the bottom line is that MTProto 2.0 has not yet been well studied prior to the work I'm going to show you. And to help us on this journey of understanding MTProto 2.0, we're going to be joined by Goofy. And Goofy is here because Goofy has some basic cryptographic training. He's learned about MACs and symmetric encryption and so on. But he kind of gets confused. And, he asks quite interesting questions, but maybe, we'll find out what Goofy thinks about the protocol as we go along. Okay, so Goofy's first question is, well, why not use TLS, right? We all know how TLS works. It's the perfect tool for this job. Why not just use it? Well, they have an answer for that. This is from their FAQ. Why are you not using X? So they have a generic answer to this question. Insert solution. So why are you not using TLS? And here's the quote. I'll read it out because I think it's kind of interesting. While other ways of achieving the same cryptographic goals undoubtedly exist, okay, they admit the existence of TLS, that's good. We feel that the present solution, i.e. MTProto 2.0, is both robust and also succeeds at our secondary task of beating unencrypted messengers in terms of delivery time and stability. So they're saying we designed our own protocol for performance reasons, not necessarily only for security reasons, right? Comments? Go ahead.
How can an encrypted protocol be faster than the unencrypted version?
It cannot. That's a very insightful question. Because cryptography costs time, right? Encrypting data takes time. One thing here you have to remember, though, is that in a messenger, we're kind of communicating at human speeds, right? So I might send a message, and then a couple of seconds will go by, you'll reply, and that's lots and lots and lots of time for doing cryptography, right? We can encrypt a kilobyte of data in a few microseconds, even faster, right? On a modern CPU on a phone. So the actual time overhead or the energy overhead of doing cryptography in the messaging setting is kind of irrelevant. It's much more relevant for a protocol like TLS, where you're dealing with many clients in parallel, and you've got thousands of clients on your e-commerce website. Then you might even go for hardware acceleration to make the crypto fast. Okay, but that's not really an issue here. So I call BS on this. Am I allowed to say that at VIScon? This is not a formal lecture. I'm not an ETH professor. I'm just a guy in a t-shirt. Okay, cool. It's complete BS, right? But let's go further. Let's join Goofy on his journey into the mysteries of MTProto 2.0. Here is the design. In the top right corner is a generic construction, which some of you might recognize. It's MAC and encrypt, right? MAC and encrypt, or encrypt and MAC. So do you remember the generic compositions for how you combine encryption and macking? You can have mac then encrypt, encrypt then mac, or encrypt and mac. Or mac and encrypt, which is the same thing, right? The order somehow doesn't matter. So that's what they chose to use. Does anybody remember generically what we can say about this construction? Encrypt and mac. Yes? It can have flaws. It's generically insecure. There are... Go ahead.
The MAC scheme is not guaranteed to give you confidentiality.
Exactly. The MAC can leak the content of the message and still be a good MAC. Exactly. You were paying attention in Applied Crypto, right? Awesome. So there are schemes that you can instantiate this construction with, MAC schemes and encryption schemes, for which this thing completely fails to give you confidentiality. Okay? I'm not saying that that's the case for the algorithms they used, but it's a bad place to start from. Let's go a little bit further. So they have this message data going in. This is the stuff that we want to encrypt. We have a MAC key and an encryption key. So the MAC key is used in the MAC, and it produces something called, their MAC output is called a message key, okay? And that becomes part of the ciphertext. So that's the value that gives you integrity. And then we have an encryption key going in here through some symmetric encryption algorithm, and that gives us our symmetric ciphertext, okay? So what we want to do is dig in and see how is this instantiated. So here is the picture. It gets a little bit complicated now. We actually don't just encrypt the message data, we encode the message data into a payload. That's very common to do something like that. Like if you remember the TLS record protocol, you have headers and so on. There's two somehow random fields, the server salt and the session ID, adding up to 128 bits. Then we have a sequence number, and this is to kind of ensure ordering in the secure channel. We have a message length field, 32 bits. Then here's the actual message data, and then some random padding. Okay, and the random padding is there to hide the true length of the plaintext. That's good. That's a nice thing to have. And this then is our payload, which goes into our actual transformation. Oh, it's unusual to get one. Oh, that's the beginning of the lecture. Okay, all right, good. So here's our MAC algorithm, and here's our symmetric encryption scheme. The symmetric encryption scheme uses both a key and an initialization vector. 10 minutes. Okay, that's perfect. Question is, where does this come from? Well, the weirdest thing in the world, we take the output of the MAC algorithm, put it through a key derivation function with some master key, and that output there is the key and the initialization vector for the symmetric encryption. So what that means is, you've missed the best bit. Oh well, never mind. Please come in and have a seat. So what that means is that for every different payload, we're going to get a different output from the MAC. We'll get a different input to the KDF. We'll get different keys and initialization vectors. So for every message we encrypt, we actually encrypt with a fresh key and a fresh initialization vector. That's actually quite good for security. It means the key is changing with every encryption that we do in a way that depends on the plaintext. But let's look at the actual algorithms that they have. They made their own MAC from SHA-256 by concatenation. Do you remember length extension attacks against MACs constructed from hash functions? Bad idea. Turns out that doesn't work here because they take the middle 128 bits of the output. Okay, so you can't do the extension because you don't have enough of the output. Like they truncate the output. Okay, still it's weird. And then here's the KDF. So we want to make a key and initialization vector. Okay, let's put the message key first and then some other key, and then let's put some other key and the message key second, and let's hash that, and that gives us key and IV. Right? So this is like some weird homebrew cryptographic algorithm, and Goofy is saying, why did they invent new MAC and KDF schemes? And honestly, I don't have a good answer for Goofy. I'd like to help Goofy, but I can't at this point. And this is not how you should... This is rolling your own cryptographic algorithms, right? Bad idea. Okay, what is the encryption? We haven't talked about what the encryption algorithm is, sorry. Here it is. They made up their own encryption mode called IGE, Infinite Garble Extension. Have any of you seen IGE before? No, you shouldn't have seen it before because it's garbage, right? It's infinite garbage extension, not infinite garble extension. Okay? It's actually a weird twist on CBC mode, if you remember CBC mode from class, for those of you who took the class. And so, it's not too far away from something we understand, but Goofy's question is, why don't we just use a standard mode? And the answer is something like the following. in CBC mode or counter mode, if I do some bit flipping in the ciphertext, then in the plain text, as an attacker, then in the plain text, I get some controlled changes. So maybe I can do bad things, right, to the plain text by bit flipping in the ciphertext. And IgE has the property that if you bit flip in some block in the ciphertext, the bit flipping, the garbling extends to the entire remainder of the plain text. And that's why it's called infinite garble extension, right? So somehow this mode has more integrity than something like CBC or counter mode. But actually it doesn't, right? So there are ways around that. By carefully controlling blocks and so on, you can do CBC-like manipulation against IgE, right? So the intuition for IgE is just wrong. They shouldn't really be using it. Okay, let's go further. You might now think, okay, so Kenny's told us everything that's going on here. All we need to know now is how are the keys, where do those keys come from for the two algorithms? How are they derived? Well, here's the funny thing. In the key exchange part of the protocol, they do a Diffie-Hellman key exchange, mod P, so there's no elliptic curves here, right? The gifted mathematicians who designed the protocol didn't know about elliptic curve cryptography, I guess, fair enough. So they're still doing old-fashioned Diffie-Hellman key exchange in a 2048-bit group. So, performance issues there. But then they take this raw shared key, g to the xy. This is the Diffie-Hellman shared value. And we're going to make keys from that. So for the client-to-server encryption, we need two keys. But one of them has actually got two components, so KK0 and KK1. So we take them like this from the raw g to the xy value. So we take the topmost 288 bits to make KK0. There's a gap of 32 bits. They take some more bits, another gap, and so on. What do you think happens in the other direction? Let me show you. Oh, it overlaps, right? They take some other selection of bits from other parts of the raw Diffie-Hellman value, but now you have overlapping key bits being used in the two different directions in the channel. What we really want in a cryptographic protocol is for the keys that we use in the different directions to be fully independent of each other, to just look like, individually, look like random bit strings and not to be correlated in any way. Okay? So Telegram fails to get this very basic property that we want for our secure channel protocol correct, fails to get it correct. This does not in itself lead to attacks, but it makes it much harder to analyze the protocol, because now you don't have different keys going in different directions in the secure channel. Okay, so Goofy says, why overlap the key bits? And why not just use a proper key derivation function instead of using directly the raw Diffie-Hellman bits? So what you could do is take all of g to the xy and use it as the random input to a KDF along with some labels to derive all the keys that you need, right? That's the standard approach that, say, TLS uses. So this is, again, is a bad design. Okay, so much for Goofy. What did we do? We actually found 4 different attacks against the protocol. I'm going to explain one of them on the next slide. The other 3 are a bit more complicated. And we went through a responsible disclosure process with Telegram. So we disclosed to them way back in April 2021. It took them a week to respond to our email. We actually had to send follow-up emails saying, did you get our first email saying that we broke your protocol? So they were not super responsive. Eventually, after a while, they acknowledged that the behaviors we had seen were correct. They argued with us about whether they were really attacks or not for technical reasons. Then we agreed to do a public disclosure on July 16th, 2021, so over a year ago now, and that's when we launched our website and we lined up some journalists and got some nice stories in the press and so on. And Telegram gave us a bug bounty. We don't do this for the bug bounties. In fact, I can't accept them. Mine go to the ETH Foundation, so so we don't do this for the money, and the money wasn't that much anyway. You could buy a nice meal in a Zurich restaurant, in some Zurich restaurants, right? So, but what I want to say here is that this looks really nice, but actually, Telegram were a little bit difficult to work with, and they actually told us they don't do any kind of security or bug fix releases. They only do bug fixes if immediately after a release, everybody's apps start crashing. Then they might fix it and push a new release quickly. But they won't do like an out-of-band release for a security issue. They wouldn't commit to any release dates for specific fixes. So what they did was they just rolled out their fixes as part of regular updates and didn't tell anybody that now your app is more secure. Okay? They made no public announcements, and they didn't issue any security advisories. They didn't wish to issue any security advisories when they were patching. When we went public, they were forced to also issue announcements on their web pages, but most of that was about arguing with us about whether our attacks were attacks or not. So this is not how to handle a vulnerability release from researchers, right? This is not really what you should do. Okay, let me show you the first and very easy attack, because time is a little bit short. It's a message reordering attack on the channel between the client and the server. Okay, so slightly different graphics here, but here's Alice communicating using the MTProto 2.0 protocol, and then the server to Bob is also using the same protocol. So Alice sends M0, then M1. That produces ciphertext C0, C1 using that MTProto transform I showed you. And here's our attacker in the middle, and all the attacker does is change the order of the ciphertext on the wire going from Alice to Bob. Okay? And these will be delivered in the wrong order to Bob in an undetectable way. So what that means is that Bob will see a different sequence of messages from the sequence that Alice actually intended to send. Yes?
Isn't there supposed to be a sequence number?
Yeah, but it doesn't work. It doesn't work because the server actually ignores the sequence number and uses the time of arrival as like a definitive ordering for messages. It's fixed now. Now they use the sequence number, but then they didn't. Yeah. And actually, if you're Bob, the rules for sequence number processing are very complicated. And as I'll say in a couple of slides' time, many clients, there are lots of independent Telegram clients, most of them got it wrong. So they didn't implement it properly. Okay, so what's the impact of this attack? Well, we like to talk about the pizza crime attack. Okay, so we have a sequence of messages. I love, it's the first message, pizza. I hate crime. Okay, that's 4 messages. So now you can transform that into I love crime, I hate pizza. Okay, and so that changes the semantics of the message flow at Bob. Now that's a trivial example. It's not really that real world, but you could maybe come up with your own scenarios for why message reordering is bad. Okay, there were 3 more attacks. I won't talk about them in detail, but one of them is an attack against the E&M construction because of the way the E&M construction works, right? Because of the idea that you might want to sanity check some fields before you've checked the MAC, and then that leads to a timing side channel. Okay, and even though this is warned against in the developer guide for Telegram, several of the Telegram official implementations were vulnerable to this attack. So they weren't even following their own implementation advice in their official implementations. We also broke the key exchange protocol, but only because we wanted to get hold of server salt and message ID, which are exchanged in that protocol. This is a very theoretical timing attack. It's very difficult to pull off in practice. Nevertheless, it shows that the protocol is not well designed. And then finally, we broke the in-CPA security of MTProto 2.0 based on its message retransmission feature. So if a message is not delivered and you don't get an acknowledgement that your message has been delivered, your app will send it again. But for reasons we don't understand, they would use the same randomness when encrypting for the second time. Okay, and what you know is like if you use the same randomness, then encryption effectively becomes deterministic, and then you can see when the same message has been encrypted twice. Okay, so that breaks in CPA security. Okay, that was the one that they argued about the most with us. They couldn't believe that they understood the concept of in-CPA security, and they did not want to admit that they had made a mistake there, right? Because this was their guarantee for their users. So anyway, these attacks are pretty theoretical, but they show you the design is kind of fragile. Okay, I should wrap up. We did a proof as well. How can you prove something if it's broken? Well, we tweaked it, right? We said, okay, what's the minimal set of changes you need to make in order to get some kind of security guarantee? The proof was really difficult because of weirdness in the way the protocol was constructed. So now when we think about designing a new protocol, we'll design it with proofs in mind to make the proofs easy. Here we were coming after the protocol design, coming up with proofs for the protocol. So it was very challenging to do. I'll skip the details here. Maybe it's just worth saying that we had to make new cryptographic assumptions in order to get the proof to go through. Otherwise, we couldn't deal with this overlapping key bits problem. That's really where that came from. So that choice of how you make the keys directly affects what we can prove about the protocol, which I think is kind of interesting. Okay, here are the proof statements, okay? Clear, right? Good. Let's move on. Okay. I briefly want to mention that as a semester project, Theo von Arx and I worked together, and we looked at this wider Telegram ecosystem, right? There are all these different independent implementations of the protocol. we wanted to ask, well, are they any good? What about their security? What kind of vulnerabilities did they have? And I'll just show you this example. This is Telethon, which is a third-party Telegram client, and we could do this attack. Okay, so this is reordering, but also deletion. We could delete messages as well from the protocol. So we could remove, please vote for me for president, and just say, I say yes to crime, I say no to pizza, for example. And you could repeat messages as well. Okay, so this is pretty bad for a secure messaging protocol. And what's really going on here is that Telegram actually encourages third-party development of apps because it publishes some kind of implementation guide. But this really attracts cryptographically inexperienced developers. That's what we saw in this project. We found 3 apps, Pyrogram, Telethon, and Gram.js, all had critical vulnerabilities in message replay and reordering attacks, and we also found a timing attack against MTProto. More theoretical. Okay, good. So, interestingly as well, as far as we know, we haven't found any kind of way in which Telegram communicates about vulnerabilities to this kind of ecosystem of developers. So they've built this ecosystem, but they're not using it as a way of sending out advice about how to implement the protocol securely. So the original attacks on Telegram that we found a year before didn't lead to an improvement in the ecosystem as a whole. All of these other apps were still vulnerable in some way or another. Okay, good. Fine. So final slide, let me just say, secure communications is something we've been doing since the time of Caesar, right, in Rome, using the Caesar cipher. Caesar's key was 3. We've moved on a little bit since then. But actually, we still have really interesting research challenges 2,000 years later. In this talk, I've only scratched the surface of Telegram. There's all those other parts of Telegram that people have not yet looked at. And the same is true for lots of other secure messaging protocols. We like to try and study cryptography deployed at scale. It provides us with interesting targets, impactful research results, and also helps us identify research problems that theoretical cryptographers, haven't even thought of yet. Because quite often developers have to solve a problem that comes to them, and they look around and they don't find any of the right theoretical tools are available for them, so they just solve it somehow. Okay, so by looking at what's happening in practice, you can actually get really interesting new theoretical problems to work on too. Okay, so we used to say don't roll your own crypto algorithms. We still say that, but we also now say don't roll your own protocol, right? So we're moving up the stack from algorithms to protocol, and actually other research that we've done on other protocols suggests don't roll your own protocol integration either. So we looked at an app called Bridgify, which had used libsignal, which is the Signal protocol as a library, and they completely messed it up. Right? So it's even possible to go wrong with very strong building blocks. You can put them together in the wrong way. Please don't use Telegram for anything sensitive. It's fine to use if you don't care about your privacy. Okay, that's it. That's it from me, and here's a slide for my group. So thanks very much for coming.
Thank you very much for very entertaining and I gained a lot of knowledge about Telegram.
Good. Are you going to stop using it now?
I will try, yes. Because,
okay.
But there are.
As
you know, there are social. Maybe that's the first question. Like, how can you convince people to switch off of Telegram?
Absolutely. Yeah.
But maybe first, we have a Q&A actually because I messed up because the picture of the schedule is wrong. We don't have too much time, but I will propose we take a few questions. And maybe if you're around afterwards,
I'll stick around outside.
Okay.
Yeah, absolutely.
Perfect.
So, are there any questions? Yes.
You mentioned you had a discussion with Telegram that it's bad resending the same message encrypted with the same key. Why is it exactly bad?
With the same randomness and the same key.
I mean, if it's the same message just repeated, couldn't the attacker repeat it itself and get the same result?
Yeah, okay, so that's exactly the kind of argument that we had with them. Good, I'm glad you asked me that. The point is that formally this leaks information that the same message is being sent twice, right? And a good messaging protocol can hide that information. Okay, so in particular, as an outside attacker, just observing the client-to-server communication, you shouldn't be able to tell whether a message is a retransmission or not a retransmission. With this attack, we can. And that might leak some useful information. For example, if the retransmission process was not automatic, it is, but if it was not, then that might leak something about the importance of that message, right? That it was retransmitted. Okay, it's a slightly weak argument, but I see you nodding, so maybe you're partly convinced. So yeah, I mean, we got into quite a long discussion with them about whether this is really an attack or not. The point is it can be prevented for free just by making sure you use fresh random padding the second time that you send the same message. So even though they disagreed with us, they still fixed the problem. So, good. Other questions?
Yeah, any more questions?
Have you had experiences with Threema?
Yes.
Oh, you weren't here at the beginning of the talk. Unfortunately, Kenny can't talk about Threema right now.
Yeah,
but he will in the future.
We've looked at Threema. Maybe if I come back next year, I can talk about Threema. Let me say one thing about Threema. Threema uses lots of nice cryptography, uses elliptic curve cryptography, and it has an end-to-end secure protocol. But the end-to-end secure protocol always uses the same key for Alice to communicate to Bob and Bob to communicate to Alice. That key never changes. What that means is the protocol does not have what we call forward security, right? And this is, this is already in the literature. I'm not giving away any secrets here. This was already observed some time ago. Whereas a protocol like Signal, the key is actually changing for every message that you send, and more or less, every time you send a message, there's a new Diffie-Hellman key exchange going on, right? So we get very strong forward security properties. So the point of Threema at the moment is that if your long-term secret ever leaked, then all of your past security is lost. All of your previous messages could have been recorded and can now be read. Interestingly, Threema also has this feature in the app where you can export your private key and store it securely somewhere. It's a nice feature, but that feature allows you to choose a password to do the encryption of the private key at the time when you do the export. So in the compelled access setting, that makes it trivial for a border agent, if they have an unlocked phone and the app is unlocked, to export a copy of your key. And now they can do that attack on forward security that I talked about and read all of your old messages. Okay? I'll say more on Threema at a future time, but that's probably enough. Thanks.
Any more questions? In 10 minutes, next talk starts, so we'll take about 2 questions maybe.
Yeah, sure.
Thank you. Is there some forward or break-in recovery security in Telegram with MTProto or with secret chats?
Can you ask the first part of the question again?
Is there forward security or break-in recovery in Telegram?
Great question. Right, so the Telegram key exchange protocol, which establishes the keys, does have forward security because it uses Diffie-Hellman key exchange, and that's authenticated using some weird RSA encryption thing, which is like what we broke. But that protocol isn't run very often. It might only be run, once a day or something. In which case, if I can learn your key now, I can decrypt an entire day's worth of information. So you can do much, much better by doing this kind of continuous key exchange that Signal does. So it's trying to do it, but it's not doing it very well. Okay.
Thank you. Is there one last question? Otherwise, I posed a question at the beginning about the social aspect of switching.
Every family should have a cryptographer who says to the family WhatsApp group, let's all move to Signal now. Now, it's a real problem, right? If you have, this is the classical network effect. If all of your friends are on that secure app, secure messaging app, that's where you will go to, because you want to know about, where are we going to drink our beer this evening or whatever it is. Or where are we going to do crime or eat pizza, right? So that's a huge challenge. And, I still use WhatsApp for communicating with some people who haven't migrated to Signal. So yeah, I totally accept the point that you're making.
All right, thank you very much.
Okay.
And also we have a little material thanks for you.
Oh, fantastic. Is it edible?
It is.
No.
It is edible inside.
Oh, okay. Well,
and you can put edible and drinkables inside.
Okay, good. Thank you very much.
Yeah, thank you very much.
Thank you. Thanks.
So the next talk starts in 8 minutes. Yes. Have fun at VIScon.